Here's a look at profit maximization. There's a well-developed economic theory of how to price products in order to maximize profits. Although it's difficult to apply this theory in practice, it does form a framework we can use to understand the concept of profit maximization, and it gives us some insight into what happens to profit as we set and change prices. First, I want to go over the terms we will use. I'm sure you're familiar with most of these terms. Some of the terms come from accounting, finance, and economics. Marginal analysis examines what happens to a firm's costs, revenues, and profits when we make or sell one additional unit of a product. Fixed costs are expenses that do not change when we change the quantity of goods we produce and sell. Examples include rent and salaries. Average fixed cost is total fixed cost divided by the number of units we produce. This declines as production increases and we spread the fixed cost over more products. Variable costs do change as we produce and sell more products. Examples are cost of goods sold and sales commissions. Average variable cost is total variable cost divided by the number of products produced. There are two ways to view average variable cost. I call the first way the accounting view because this is how it's explained in most accounting books. The accounting view treats average variable cost as a constant. It does not change as the quantity of goods increases. As output increases, total costs are viewed as increasing at a constant linear or straight line rate. Think of how total cost is shown on most break-even charts. You'll see what the accounting view of average variable cost looks like. On the other hand, the economics view of average variable cost, which you find in most econ books, sees average variable cost as having a curvature. As output increases, the average variable cost declines, it reaches a minimum, and rises thereafter. Here's an informal explanation of that pattern. When output is low, you're not very efficient, so the average variable cost is higher. As output increases, you start getting more efficient, and this brings the average variable cost down. As output continues to increase, at some point you become less efficient, causing average variable cost to increase again. Marginal cost is the change in total cost when you produce and sell one additional unit, and marginal revenue is the change in total revenue obtained by selling one additional unit. This is an explanation of marginal revenue. The starting point is price A. The price is $100, and 1,000 units are sold, so the total revenue is $100,000. According to economic theory, the way you sell one additional unit is to lower the price just enough to sell 1,001 units. In this example, the lower price is price B. It equals $99.99. And when we sell 1,001 units at the lower price, the new total revenue equals $100,089.99. Total revenue increased $89.99, and that's the marginal revenue. In this example, the fixed cost is $400, and the average variable cost is $10 a unit. Since average variable cost is a constant, this example uses the accounting view of average variable cost. The columns are for price, quantity sold, total sales revenue, which is price times quantity, total cost, and profit. For simplicity, this is a straight line demand curve. Take a look at the total revenue column and notice that it starts at zero. The price of $60 is so high that we don't sell anything. As we lower the price, we start selling a few units, and the total revenue starts increasing. Once again, the price went down and total revenue went up. What does this tell us about elasticity of demand at these prices? Price and total revenue are moving in opposite directions, so demand is elastic. As the price goes down, total revenue continues to increase, so demand is elastic until the price hits $30. At a price of $30, the total revenue is at its maximum of $900. When the price goes down to $25, total revenue declines, so demand becomes inelastic. Total revenue continues to decline as prices go down. Remember I said this was a straight line demand curve? Earlier I mentioned that it was incorrect to describe an entire straight line demand curve as being elastic or inelastic. This example demonstrates that fact. Now look at the profit column. When the price is $50, we break even. As we lower the price, our profit increases. A price of $35 produces the maximum profit of $2.25. When we reach a price of $20, we have another break-even point. And prices lower than $20 produce losses. There are two important lessons from this example. First, maximum sales revenue of $900 and a price of $30 does not maximize profit. That comes from a price of $35. Second, there are two break-even points. One because the price is too high, and the other because the price is too low. Somewhere between the break-even points is the sweet spot of maximum profits. Next, we're going to use this same example and look at a graph of total revenue, total cost, and profit. The red line shows total cost. Remember, this example used the accounting view of average variable cost, so total cost increases as a straight line. The blue curve is total revenue, and the green curve is profit. I've circled the two break-even points, the point of maximum total revenue, and show that the maximum profit occurs when we sell 25 units. In this example, the average variable cost is not constant. It starts high, then declines, and eventually increases again, so this example uses the economics view of average variable cost. I calculated these values using formulas in Excel and rounded to the nearest dollar, so there is some rounding error in the numbers. But we see the same basic pattern. Total revenue is highest when the price is $30, there are two break-even points, and profit is maximized when the price is $35. This is a graph of the example. Notice that the red curve, that's the total cost, increases as a curve. Profit is maximized when 25 units are sold. As you may recall from economics, profit is maximized when marginal cost equals marginal revenue. The slope of the total revenue line, that's the blue line, is the marginal revenue, and the slope of the total cost line, that's the red line, is the marginal cost. If you drew tangents to the total revenue and total cost lines, the tangents would be parallel at 25 units, the point of maximum profit. So if you think your marginal cost equals your marginal revenue, don't change anything. You're at maximum profit. That's a look at profit maximization.